part, our panel discussion on azo-diarrhea. And I'll hand you over to Daniel, and then Bez, and then Eduardo, who will be talking through the final points.
So thank you for coming. We are good by Israel, and we are the UCL iGEM philosophical team. So iGEM is, in case you don't know, most of you probably don't, iGEM is a systematic biology competition which aims to create a biological device, so using a biological organism, and modifying it genetically so that it can produce a useful output or do something useful, essentially. It's an international competition that has, I think this year it's around 2,250 teams from all over the world. So we're going to give a little introduction of what our team looks like. That's us. We all come from biosciences kind of backgrounds. We have some social scientists as well, but the rest of our groups are molecular biologists and synthetic biologists and biochemical organisms and stuff. And our ages do range from very young, like us, to older, like people finishing with PhDs and stuff. So you probably have guessed from our title who that is, that we're focused on the project and things like that. So what are azo-dyes? Azo-dyes are synthetic colorants. They were first synthesized back in the 1900s, and they were a total revolution in the textile industry because they're so good. They're such good dyes with really little quantity. I'm going to do a demonstration of this. This is food coloring, which is azo-dye. We just bought this on Amazon. We just put this glass of water. Hopefully, swap it around so it gets a really intense red colour. See that? They're really, really powerful, and they attach to clothes really well. So they're really good dyes. They're really stable, chemically stable, in control conditions. So they're really good. But they might present some environmental problems related to the diagnosis and we'll come back to that later. So the range of applications of azo-dyes is very, very, very wide. You get from food coloring, not just M&Ms, but like all sorts of stuff. Even micro-3Ds and cosmetics, interior design, all sorts of stuff. But I would like probably the most important application of azo-dyes is textiles. About 70% of the whole dye manufacturing goes to textile industry, especially the textile industry. So we said before that azo-dyes are pretty stable, but due to the nature of the dyeing process of the clothes in textile environments, they might present some environmental problems. So we're trying to simulate, in a very simplistic way, how industries dye clothes. We just get a huge bucket of azo-dye water, and you just take your clothes in it, and you take it out, and it's coloured. And the clothes are coloured, but there's still dye in the water. And the problem comes from how to get rid of that, because there's not really an efficient way of getting rid of the azo-dyes in the water. So usually what companies do is just chuck them out into the environment, and that can cause some issues. We're talking about concentration of 10 to 50% of the dye is not attached to the clothes, it remains in the water. And they are really, really highly soluble, which is demonstrated. So they can propagate really quickly through aqueous environments like rivers and sewers. And the main problem deriving from azo-dyes is their potential degradation. So there's several ways why azo-dyes might get degraded in the environment. You can get degradation because of bacterial strains present in the river, or because of photo degradation, like recently something like. But the point is the products of the degradation can be really, really nasty, like aromatic amines. Aromatic amines are a serious potential carcinogenic, and they can be effectively a threat to wildlife in rivers and also to humans. So because of this, there's a series of regulations in terms of industry of how much dye you can get into the water, volumes, concentrations. So there's many dyes have been forbidden in many countries. and India are another story, because their regulation is not as strict as those of the rest of the world. So that's one of the reasons why they are one of the users of textile products and also of dyes themselves, because the regulation is not strict, so pollution can be enhanced. And I think this slide highlights what we're trying to tackle with our project. We're basically trying to generate a device that is able to, through a series of enzymatic reactions, I'm going to go into a lot of detail, get rid of the azodyes in an industrial environment before it goes into the river. So that's what we're trying to do, basically get an industrial approach to bioremediation of these azodyes contaminated water. And now Ben's going to go over the current methods of treating azodyes.
So after identifying the problem that we want to tackle, we looked into what the current methods used to dispose of azodye effluents. So in industry at the moment, it's mostly physical and chemical steps. The physical steps tend to be adsorbing the azodye effluent to solid materials such as carbon and wood chips. And the problem with this is it generates a sludge kind of material which you then need to deal with separately. So it doesn't really solve the problem, it more just removes it. The chemical oxidation is another option, but it tends to be quite costly and energy intensive. Sometimes it's not really feasible on an industrial scale. So our solution is a biological solution. So what we're doing is we're using enzymes from 4 separate species, 3 of them are bacterial and 1 fungal. And we're taking these enzymes which occur naturally and incorporating them into a single plasmid. This plasmid we're then integrating into an E. coli bacteria, which will produce these enzymes and allow us to degrade aromatic and azodyes to reduce their toxicity and potentially produce useful products. So a large part of our project is working with industry and really gearing how our process works towards their needs. So we went to ATAN in Basel, which is an association of dye and pigment manufacturers who are working towards a more ecological and sustainable industry. So what we got from them were specific dye concentrations which they work with and individual dyes which are more concerned to them. So from this information, we've developed a bioprocess which we've targeted as an end-of-pipe solution to their textile plants. We're able to control the state of degradation and gear towards what they need and integrate it in the process they have in place already. And the important thing about this is our bacteria are contained within this bioprocess. We do not intend to be releasing these bacteria into the world at all. Having said that, there's always going to be a risk of bacteria escaping, which I know is a concern to lots of the public. But we've implemented a series of biosafety techniques to make sure this does not cause any additional problems, which everyone's going to talk to us about now.
So, as Beth mentioned, we will have a physical constraint that will keep our bacteria in a separate environment from the natural environment. But sadly, we are still using genetically engineered bacteria, and there is a lot of concern of them being released or split into the environment. The safety measures cannot always be 100% secure. So, and once they are released into the environment, they can cause there are concerns about them causing different harm to the environment. One of them can be outcompeting the natural environment. So if you have a bacteria that has been evolved extremely fast, in our case, and that can outcompete the rest of the population of living organisms in the environment, that can cause an issue. But the main problem that causes concern in the population is that the DNA that we use can still split into the environment, and we have not complete knowledge about this information splitting into the environment. And we want to make sure that we can keep it in a constrained situation. So, and because one analogy of what we mean by biosafety. So, as most of you might know, if you cycle in London, there is a very, very likely option that your bike might escape you and just be taken away if you don't have a lock. So, a lock is what we use as a safety measure to avoid our bike to go wild into the environment and be taken by someone else, most likely. And in terms of biology, what we want to do is put locks to this bike, make sure it stays there. And with only one lock, but possibly more than one lock. For example, here for my bike, I use a lock for the front wheel, and it's a like hiding front wheel. I think I'm going to take it. And in biology, what has been done, what has been approached by previous teams and by scientists around the world is so far biological kill switches. So programmed suicide inside the cell. So once the cell has done its job, in our case it would be degrading azodyes, you have the option of inducing the suicide of the cell. So program the cell to release a toxin by herself that can kill it at the end of its job. Or what we also thought is to, since our project will still be in a longer term, think of a longer term solution to biosafety. So a way to make sure that our bike doesn't get stolen would be what this clever designer and novelist thought. So instead of just adding locks, you can embed the biosafety, the safety measure into the bike. So you have this bike which is hugging the pole and making sure nobody takes it away. And what is hugging the pole in biology? We thought about xenobiology. So you're not just adding locks to your bike, you're changing your bike, you're changing your living organism to make sure it doesn't leave the pole. Or in our case, it doesn't leave our bioreactor, our enclosed system. And there are different levels at which you can implement this change into the organism. I won't go through much in detail, but what you have to know is that these first two mechanisms are mainly to avoid the spread of DNA. So we said that DNA, if it goes wild into the environment, it can be an unknown. We don't know how to tackle it. So this brings new amino acids, new DNA vectors, which are unrecognizable by living organisms on Earth. So even if it goes into the environment, nothing on Earth can understand what it's saying. So that would tackle the problem of the DNA spilling. And these, we call it metabolic firewalls, so something that avoids the bacteria to spread into the environment from the metabolic point of view. So all of us, for example, need vitamins. And the same way we need vitamins, bacteria also need vitamins. And what we aim to do is to adapt the bacteria to only survive on a synthetic vitamin, something that cannot ever be found in nature. And therefore, these synthetic vitamins will be derived from our azodyes. So while the bacteria is degrading the azodyes, it's also using them to survive from its very core of its biochemistry. So without this special environment you can only find after a dying factory, these bacteria cannot find anywhere on Earth where it can find what it needs to survive. I guess we went through most of our projects, and we want to lead now to the discussion, and Bez will introduce.
Right, so the main purpose of this event today is to have a discussion about not really the feasibility of our project, but more the ethical implications it may have, and things we need to think about when employing synthetic biology in situations such as azodite pollution. So our first question, which we want you to be involved in, but first of all, can we just have a quick show of hands? Who is a student? Okay, and who is working in academia? And have we got anyone from fashion and textile industry? And any environmental? Excellent. Okay, so our first question is, how do you think the problem of azodyes should be tackled? Should we be employing synthetic biology approach? Should we, I suppose, we could think about getting rid of them altogether? Or I suppose we could think about using alternative solutions? And we're wondering if any of you had any thoughts on that. Yeah? Oh, I'm sorry, I'll bring up the mic.
I can shout.
Go for it.
Thank you. I think, from my perspective, as someone who, I should say, I'm a PhD student in the Faculty of Law's, looking at the regulation of technologies, and also a bit of an environmentalist, and someone who's fairly interested in sort of ethical consumerism, especially in the fashion industry. My initial reaction to tackling this problem should be kind of coming off azodyes as opposed to eating them after they've been used. And by that I mean finding alternatives. So for example, there are several fashion labels that do sort of dye their clothes sustainably. They don't use water and they use less harmful dyes. So suppose from my point of view, rather than kind of going into risky territory of trying to solve one technology with another technology and a very uncertain new technology, we look at what we already have and try and sort of get off the azo die habit by employing less harmful solutions to do the same thing, so you don't have the end of pipe problem, or you've got less of an end of pipe problem. Oh, I should say though that this sounds really fascinating as well. If it did work and it was safe, then I'd be behind that as a kind of. But I think it should be one of a series of measures that tackle the problem from all directions.
Okay, that's right. It's a very interesting point. I don't know if anyone from our team has anything to add to that. Sahil?
Yeah, I would just say, right now though, there's already so much of it out there that a remediation strategy might be a good idea because of the fact that, like Daniel pointed out, the like India and China, for them, it's already out there. It's polluting their systems, and regulations are harsh. So aren't harsh. I mean, so yeah, I think if you sorry. Did anyone hear what I said? Okay. Yeah, so I think since the problem is already there, like a solution that's not remove the problem is kind of necessary. But yeah, I agree with you also. Yeah.
Coming back to that, this question for everyone really. If the idea is to move away from AZIs, how would corporations be encouraged to do that? What would make them, I suppose, change their tact? This is a question for everyone, really.
So really, without public pressure, what is the incentive to feel for companies to actually change what they're doing to perhaps dye them more expensive? What, as the general public, do you feel should be the strategy of people who, we know that there are these carcinogens in nature, we know that they're in our water supplies, they're in animal supplies, so what, as a general public, would we give as an incentive to these companies whose job it is really just to make money? What incentive do they have to actually change dyes if that is what we propose?
Okay, one. I guess you have to prevent them from being able to use azo dyes in the first place. And I guess the danger of being able to soak up what's already out there means it gives companies an excuse to go, well look, we're going to clean up our waste, so there's no problem with it. So I think the only way to prevent use in the first place is to penalise them for using azo dyes or ban azo dyes in the first place. Because otherwise, like you say, they exist to make money. And unless consumers are going to pay more for goods that are essentially exactly the same, but better for the environment, there is no incentive. So you have to literally cut it at the source.
It's not an incentive, it's a punishment.
Yeah, it's punishment.
But then the azo dyes themselves aren't toxic, it's just the waste. So does that still mean that we should get rid of...
That's been taken over.
Just saying, I think that you need to put a limitation on how much waste product the company can produce, so that they are forced to ration how much of the azo dyes they use, or think of ways to get rid of their waste product. It might mean that they start using azo dyes and another type of dye, maybe, if they've got a regulation of how much waste product can come out of one kind of factory. Does that make sense? So similar kind of punishment.
We think that. That's
So pass the money to
Yeah.
Thanks. I think the polluter pays principle is a really good one, as you suggested, and there's been some research about how to get companies or farmers off using pesticides, which is a kind of comparable problem. So if you can get it through, if you can get it into the law, then polluter pays principle can be really effective. You can also subsidise less harmful dyes. again, if you can get that through law. And then there are various sort of physical things you can do. So you can require companies to have their waste pipe upstream from the water intake pipe, which is a massive incentive for them to clean the water before they then use it for their processing.
Just one point, I should declare I kind of technically am an environmentalist, though I'm a sustainability advisor. So I guess one of the things so I work at an organisation called Forum for the Future. We're slightly different. We're not campaigning. We actually work with businesses to solve some of these big problems. The one thing I would say about, I think you're totally valid, those solutions. I think that depends on a really stable regulatory environment and one where regulations are taken seriously. Which, China has some of the best regulation out there. It just doesn't get practiced because of the way it's kind of policed and regulated. So the way we tend to work is that you kind of have to find another way of making this a business's worth their while. And it's usually the ones that are kind of pioneering have a reason that's beyond just kind of commercial incentives. And I kind of take your point, like 99% of business out there is probably about just making money, but it's those ones that can find those innovative solutions that might be the alternatives to the dyes, or could be the kind of new ways of doing this, which, there are people, it might be people that are sponsoring some of your research, to be honest, that are looking at these things. And it's sort of about getting those guys to be the pioneers, to show the way in which it can be viable, and then to bring it to scale to make sure that you've got the kind of economic efficiencies that azo dyes clearly actually provide that other dyes don't. So I guess it's just a kind of word that regulation can't be relied on its own globally.
Yeah, I'd like to echo that, and also just point out that regulation and that sort of thing, they have costs, and regulation has costs, and it will be expensive and difficult monitoring, enforcing has costs, and people who have to switch to alternative sources, that will have costs for them, for their businesses and the consumers of those products. This seems like a really sensible, neat idea, but it's hard to have any kind of real understanding of what the solution would be like in practice from a short slideshow. I mean, do you have any idea about what the cost of this would be relative to regulation or other options? Is this sort of effective or feasible for a company, or is it something further on?
Well, it's something we're currently investigating at the moment, and it's a big part of our project to understand whether it's feasible financially and whether it really works as well. And that's what we're doing this summer, I suppose. We're showing how the science works and investigating whether it's financially viable as well.
Just to mention, Joy up there, these are our bioprocessing guy, and he's designing the entire bioreactor system as a full product to add on the end, literally just be an add-on on the end of the battery. So we are modelling the whole bioprocess, how much each stage will cost, and whether we can get lucrative produce out of the bioprocess in the end, so that even if it does cost, they can regain some of that money from the products that we filter.
Do you know what the process does the process itself have other impacts? I mean, does it use water or other products, or metals, rare earth metals? Are there any sort of associated impacts from these?
Yeah, well, the idea would be to be able to create incentive where companies and businesses want, so from a financial perspective, being able to basically show that they can not only save the environment in that sense, cut down their toxicity, like whatever they have to emit from the water streams. Not only do that, but at the same time find a way to make money out of it. So the idea would be to reuse as much from natural products as possible. So one of the ideas that we had, looking at the YSB event that we had a couple of days ago, was to collaborate with Imperial, who's actually, at this point, developing some kind of membrane to basically filter out the breakdown products or the azo dyes. And that would be purely out of cellulose. So that's, again, showing how we can use alternative technologies, both to the advantage of the environment and the business.
But as to the amount of water that we use, there is, obviously, with any bioreactor, the main problems with azo dyes at the moment is that they use so much water in the actual dyeing processes that companies are using things called sulfonated dyes more often because you have to use less water, but they're the most dangerous dyes because they don't break down in the processes that we showed you that they're currently using. So by using our process, they can use the sulfonated dyes and hence not have to use so much water in the process, so it kind of balances the scales with our reactor at the very end.
So one of the enzymes that I mentioned earlier is from a fungus which is specifically targets sulfonated dyes. That's something we got from industry, that they wanted sulfonated dyes degraded especially, and hence why I found that enzyme used in our process. So we've got any other questions?
I guess regarding your question is, our work will be more of a proof of concept. It's in our interest to actually understand if it's more feasible, but rather than focusing on, yes, it's interesting and it will be important to understand if it's cost feasible. That's what we decide because in the industry. But right now our question is, even assuming that this work isn't ethically, but we get to use it. And we're doing all we can, looking into industry, understanding what their actual systems are right now, how to be able to embed it simply into their system without having to change the entire industry to be a faster solution than most of those. So summarizing what we were talking about in the first part of the debate, we had this slide which wanted to kind of summarize where the responsibility lies in these environmental issues. We were talking at the beginning, where are the governmental and how is the legislation right now? So it can be the two bottlenecks are in banning the most toxic azo dyes and reducing the limits of wastewater that can be released. And those have been implemented, but as you have pointed out, there can be issues with the regulatory systems. And on the other side, the industry, from their own point of view, can implement systems to use less water and produce less wastewater. But of course, there must be a push from the consumer, and we kind of all are responsible in some sense of pushing towards the industry to change their ideas. But what I wanted to move more from is, as you could see in this picture, there's this guy who's the scientist between these four pictures. And if you go back to him, is Sir William Henry Perkins, and he was the inventor of the synthetic dyes. He was working in his lab, as he was working days and nights in his lab. He made the end of his house, like in a room that he turned into a lab. And working days and nights, he was trying to make quinine, which is an anti-malarial drug. This drug has been only synthesized about 10 years ago, so it was 150 years ahead of his times. But still, while he was tinkering with chemistry, he came up with this very colorful material, which we cannot see here. He might have come up with some powder similar to this. And instead of doing like all the other chemists of the time, he went to his sister cupboard, took her silk dress, dipped it into the dye, and so it was a perfect synthetic dye. That's what the queens and all the ladies of the time were looking for. The thing is, when he was developing this new technology, he didn't really think of what were the risks associated with how could this become an environmental issue. And we were also, skip that, we'll go to that later. So we were also wondering, following from that, what is our responsibility as scientists in developing new technology? As you said, there is the risk of developing a new technology for the previous technology. And we want to bring about the responsibility of the scientists in this decision, where there is and how can it be.
So,
I think there's quite a lot of responsibility. I mean, the story you're talking about now, when you invented the first purple dye, at the time when a lot of the natural dyes were being used on a mass scale, that also meant mass slavery and the time-consuming process that took to produce the natural dyes